We have a recorded presentation from Linjian Davey from Alibaba Cloud with a tale of forgery and determined detection work. So the Q&As will not be after the presentation here, but you can continue the discussion in the Mattermost workshop channel for that. And please don't forget to do the polls.
Hello everyone, my name is Davey, and I'm from the networking infrastructure team at Alibaba Cloud. I'm sorry I cannot come in person and hope we can join this workshop online in this way. The primary responsibility of our team is to ensure the stability and the security of Alibaba's networking infrastructure, supporting cloud services and popular applications such as AI and short video platforms. Before this talk, I would like to share some background. Over the past 2 years, I've led a team focused on tracking and addressing DNS anomalies, because during our daily operations, we often receive our customer requests related to DNS issues. These issues typically fall into 2 main categories. The first involves no response scenarios, often tied to our own DNS system, such as during DOS attacks or sometimes software crashes due to some reasons. The second one, more complex category, involves forged answers, where debugging the DNS forged answers and hijacking is particularly challenging. And today, I would like to share some experience from our troubleshooting DNS hijacking cases. Before diving into the DNS hijack cases, let's first go through quickly how DNS works, which I'm sure most of you are quite familiar with. In essence, the domain name system acts as the internet phone book, translating human-readable domain names into machine-readable IP addresses and other network resources. As shown in the diagram, when a user wants to visit foo.com, their devices queries DNS reserver, either self-configured or signed by the network provider. The reserver then acts as a proxy, recursively query the authoritative server down from the root server, the com server, and finally to the foo.com server. It returns the reserved IP address to the user. The user can then connect to that IP address. It sounds straightforward, but debugging DNS issues can be surprisingly complex. Despite being invented over 40 years ago, many people still find the DNS troubleshooting a challenge when something goes wrong. Before the user receives the correct answer, numerous DNS interceptions and communication occur. This communication can be intercepted because most of the DNS queries and the response were not encrypted. Additionally, DNS answers cached by the reserver can be poisoned as well, because not all the DNS systems support DNSSEC, which we call it DNSSEC enabled. On the authoritative side, the DOM data can be hacked too. It was recently discovered that DOM hijacking and the name takeovers happens. They are possible on major DNS platform that share the same name server clusters. Finally, the user might receive a forged DNS response, potentially with redirected to a malicious website that could contain malware or steal credentials of users. Debugging these issues is extremely challenging, especially when trying to identify who forged my DNS answers. By the end of 2023, we met DNS hijack cases. My team successfully helped a customer resolve a critical issue where their website were being redirected to a gambling website, resulting in monthly loss of millions. Here are 3 key steps we took to resolve the problem. Firstly, we used hundreds of our probes to replicate the issue and confirm that the DNS response was being forged in a specific area. By editing the host file and changing the victim's domain to the malicious IP address, we are able to print the redirected malicious page on our screen. Secondly, we discovered that certain queries to the root and the .com servers were receiving random forged answers. To address this, we developed a tool called DNS Traceroute, which tracks the path of DNS query to identify the source of the hijacking, similar to how a traditional traceroute command works. We will explore that part in more detail later. Finally, we reached out to the responsible parties and work closely to identify and resolve the issue. Based on our experience, some domain names had been forged due to anti-fraud measures imposed by authorities, but not all cases were handled in such manner. The more detailed information you can provide to the relevant parties, the more seriously they will take the issues. Okay, that goes through the process how we debug the problem. Firstly, we use dig command. The command with trace option can mimic what DNS resolver does when it looks up a domain. It starts at the root server and then query the next level of domain, name servers, and so on until it's reached the authoritative name server for the domain. As the diagram shows that when the client digfoo.com with the trace option, it only receives DNS referral until the foo.com authoritative name server provides a DNS answer. Usually, the DNS referral means the server does not have the answer. You need to ask the next one. When we query the victim's domain with the trace option enabled, we found that both the root and the .com authoritative servers occasionally return a DNS response containing an A record. This was the root of problem. The DNS response from the root and the .com authoritative servers were being intercepted. The forged answer were then cached by any resolver that speak to them. We tested different domains to observe the interception behavior, and we discovered that the DNS interceptions were specifically targeting certain victim domains. However, we still face significant debugging challenges. What happens in between? Who forged the answers? There could be multiple paths between the testing client and the root or the .com servers, each with multiple hopes. It would be incredibly helpful if the device in the middle could reveal where the issue occurred. We were inspired from how the traceroute command works. The traceroute command pins each network device along the path to identify where the issue occurs. It works its magic by manipulating the TTL field in the IP packet header. As the IP packet is forwarded by each router, the TTL is decreased by 1. Then the TTL reaches 0, the packet is discarded. And the TTL exceeded ICMP message is sent back, revealing the IP address of the router that discarded the packet. The traceroute can also use the UDP on port 53 to test if the packet are being dropped or not. However, it wasn't helpful in our case. So we are confident that the interceptions along the path is able to read the QNAME of the DNS query, which means only the DNS query with the victim's name as the QNAME will be intercepted. Intuitively, we developed a DNS Traceroute tool. The key difference between the DNS Traceroute and the conventional Traceroute command is that DNS Traceroute uses the IP UDP DNS packages with the incrementing TTL instead of IP ICMP packets. As shown in the diagram, the testing client continues send DNS queries with the increasing TTL from 0 to 13. It collects all the ICMPs and the DNS response received during the process for further analysis. Suppose there is a bad guy in the second hop of the path who forges the DNS response, targeting a specific queue name. This is a simplified model of the DNS hijacking in our cases. The client sends a DNS query with the increase in TTL value and receives the forged answer when the TTL reaches 2. At the same time, it also receives TTL exceeded ICMP messages. As the TTL continues to increase, the client will keep receiving both the forged answer and the TTL exceeding ICMP messages. This indicates that the DNS hijacking is happening through on-path interceptions. In this scenario, it's mostly likely that the DNS traffic is silently monitored, is silently listened by some bad guys. Normal DNS queries are either dropped nor modified, but forwarded to the destination server as expected. The forged DNS response received by the client before the real response from the legitimate server. This is a real example of on-path interception that we used our tool to print the result. The trace results show that the first forged DNS response was received when the TTL reached 10, and we pinpoint the attacker's IP address. You can see that the two heavily relied on ICMP messages. In another DNS hijack case, we observed that the devices in the middle can disable the ICMP messages, which weaken the tool's effectiveness. Okay, let's wrap up the troubleshooting result we had found. Firstly, we did with the trace option find specific DNS query to root and the .com server receive random forged answer, which will be cached by the reserver. Then the DNS Traceroute tools print the path of the query forwarded and pinpoint the IP address who forged the answers. The DNS Traceroute tool reviews on-path interceptions by detecting when the hijacked device responds with a forged DNS answer before the legitimate response arrives. In the end, I would like to say over the past years, our team continued to trace the behavior of these DNS interceptions. We noticed that this technique is widely adopted on national scale as a security measure, often used to prevent the abuse of DNS, as I mentioned. However, it can also be exploited for malicious purpose, much like a hole in the wall concealed under the guise of the legitimate network management. So, the DNS Traceroute tool we developed helped us to pinpoint the exact source of the attack, which significantly enhanced our ability to collaborate with the authorities and relevant parties to resolve the issue. That's the end of my presentation. Thank you for your time. If you have any questions or would like to discuss further with me, feel free to reach out to me via email. Thank you.
So as Davey says, the questions will be in the Mattermost workshop channel. Don't forget to rate the talks.